Let's briefly discuss solids. There's two main classifications we're going to look at here, crystalline solids and amorphous solids. So what's the difference between the two? Well, crystalline solids are going to have things that are in a very orderly array. They have flat, well-defined surfaces. We call these surfaces faces, and so they're very flat, they're well-defined. So I'm going to try to do this so that you can actually see. So here, all right, here is a crystalline solid. You can see where it's got very flat, well-defined faces. Even on the portions that are cut, if you look, it's kind of goes down further into the crystal. All right, here is another crystalline solid, where you can see those flat, well-defined faces. Let's see here, these two. The first one I showed you is calcite. And the second one I showed you is gypsum, also known as selenite, okay? Whereas an amorphous solid, things are in a random jumble. You're not going to get those nice, well-defined faces. And so when you cleave a crystalline solid, it's going to break on those nice faces. An amorphous solid, because it doesn't have those faces, when you break it, it's going to shatter in weird patterns, okay? This one is bauxite, okay? And you can see here, it's kind of got these blobs in it, and when you look at the edges of it, where it's broken, all right, it's not got those nice, well-defined faces. And so everything here is done in that random jumble. So it's a mineral identification kit. During COVID, it wasn't just chemistry that had to figure out how to do lab work online. Biology had to, geosciences had to, and thanks to all the teaching I do, even though I teach chemistry, I was given one of the geosciences remote lab kits from one of the campuses I teach on. So I can utilize that in my teaching, such as this. So those are from that. That's why I had the identification list. But so the crystalline and the amorphous solids are characterized very differently because of that. And so when we look here, all right, so here's two pictures. Okay, which one do you think is which? The top picture, is that the crystalline or the amorphous solid? It's the amorphous, okay? All right, and that bottom picture, is that crystalline or amorphous? That's the crystalline one. All right, and so you can see that the crystalline one is nice, ordered, well-defined, everything, has its little spot, but the amorphous one is just kind of all over the place. And when you look at the physical pictures of each of those, not just the crystal structure picture, you can see where the crystalline one has those nice, well-defined faces, whereas the amorphous one does not. And then again, when we cleave these, so our crystalline solids, if you break them, they'll break on those nice lines. But our amorphous solids, if we break them, they're just going to shatter into a crazy pattern. That's why if you break glass, glass is amorphous. If I drop a piece of glassware, it shatters everywhere. All right, this mirror, it's amorphous. And so we can look at the classifications of our solids here. We can start off with crystalline solids. I know this is kind of small and off to the side, but I have to juggle showing the images with, making sure my face is in the corner there. And so when we look at our crystalline solids, all right, this is just looking at crystalline solids, not the amorphous ones. But within crystalline solids, we can break these down into several different headers: molecular solids, ionic solids, atomic solids, okay? And then we can break those further down into a whole bunch of other different categories as well, okay? When I look at these and I look at our different types of crystalline solids and I relate that back to our intermolecular forces, our molecular crystals, those are held together by our dispersion forces or our van der Waals forces, and hydrogen bonds. They're going to be softer. They're going to melt lower temperatures. They're not going to conduct electricity. So things like water when it crystallizes. When I look at network covalent, now this is interesting. So we're used to covalent molecules being held together by those intermolecular forces. But if you look at the network covalent or the covalent network, the intermolecular forces are covalent bonds. These are very hard, very high melting points. So what's happening here is that It is a whole array. So instead of having individual discrete molecules held together by those intermolecular forces, we have a whole array that stretches across of covalent bonds holding everything together in that three-dimensional solid. So things like diamond, that's network covalent. That's why diamond is so hard and so hard to melt, is because it's network covalent. And then of course we have metallic solids, so our pure metals, and then ionic compounds, brittle, high melting points. These are held together by electrostatic forces. And so when I look at these three right here, those are all bonding forces, all right? And so they're going to have a variety of different properties. Metallic, the bonding forces there are definitely not as strong, and so some of them are softer and have lower melting points. They all conduct because it's that electron C, right? And so we've got that delocalized electrons everywhere. And so we have all sorts of different types of crystalline solids that we can get a variety of different properties from. And then crystalline solids, personally, I love crystalline solids because I love looking at crystals. So this slide entirely is just showing you some different types of crystalline solids. So some of them we can get different faces. They can be square, they can be rectangular, they can be rhombic, they can be hexagonal. So the well-defined faces doesn't mean it always has to be a square or a rectangle. We can get all sorts of different types of faces depending on the type of crystal structure that exists inside of the individual substance. And so there's all sorts of different crystal structures and things that we call unit cells that have to do with how things crystallize out and the solid properties that they have. So anyway, that's our solids. And so hopefully, seeing the pieces of rock can help you understand the difference between the crystal and the amorphous. If you are in one of my classes where you see me for lecture on the computer, but then you do see me for lab in person, I'm actually going to bring the rock kit with me to class. So if you want to examine some of the different types of rock and see the difference in your hand of the crystalline versus the amorphous solids, I will have those present. If you're not in one of my classes, I'm sorry, you can only look at what I held up to the camera because I obviously cannot pass you a sample of something through a camera. So those are our solids.